Back to the deep dive. Ready to get into something pretty cutting edge today.
Absolutely. Sounds like we've got some interesting material.
We do. We're looking at MambaNeXt-YOLO, a new approach in real-time object detection. We've got the usual collection of notes, paper details, study guides, all the good stuff you sent over.
Right.
And our mission, as always, is to really unpack it, understand the core ideas, what makes it innovative, and why it's getting attention, especially for real-time and edge computing scenarios. We want those key academic insights.
And maybe find a few surprises in the details. It's definitely a hot area. Real-time object detection is just crucial now.
Yeah, I mean, you think about autonomous driving, surveillance, robotics, even things like UAVs assisting with networks like the notes mentioned.
Exactly. And the core problem hasn't really changed. You need speed, you need accuracy, and often you're working with hardware that's, well, limited. Power constraints, processing limits.
It's always that trade-off, isn't it? Speed versus accuracy, especially on the end. And the sources kind of walk us through the history a bit. They mentioned the YOLO-series, YOLO V3, V4, V5, up to what, V8, V10, V11, V12 in these notes.
Right, the YOLO family, they really were pioneers in finding a workable balance. They became, the go-to for being fast and pretty decent on accuracy for a long time.
They set a benchmark. But the source material points out a limitation, right? Something fundamental about their architecture.
Yeah, their heavy reliance on convolutional operations, CNNs. CNNs are fantastic at local details, textures, edges, patterns right next to each other. Really good at that fine-grained stuff.
Okay.
But because they focus locally, they struggle to capture global dependencies. Understanding how different parts of a scene, maybe far apart, relate to each other, that's harder for a standard CNN.
So it's like they're wearing blinders, seeing only a small patch really well. And that's where Transformers came out. They were meant to solve that global context issue.
Precisely. Transformers, with their self-attention mechanism, are brilliant at modeling that global context. Seeing the relationships across the whole image or sequence, huge leaps in NLP and vision, too.
But there's always a but.
There's always a but. The cost? Computationally, self-attention is expensive. It scales quadratically ON2 with the number of tokens or pixels. For high-res images, that quickly becomes, well, impractical for real-time performance, especially on edge devices with limited juice.
Okay, so we hit another wall. CNNs, fast, local, miss the big picture. Transformers, see the big picture but too slow, too power hungry for the edge because of that n squared cost. Seems like we need something else.
Exactly, and this is where state space models, or SSMs, have become really interesting recently. They offer a different way to model sequences, and the key advantage is their linear time complexity, just ON, much more scalable.
Linear time. Okay, that sounds promising for efficiency.
Very promising. And the sources specifically call out Mamba. It's a type of SSM that introduced this idea of a selective state space mechanism. You can think of it as giving the model a kind of smart, efficient memory. It can learn what information is important to keep track of over long sequences without that quadratic overhead.
So Mamba gives you that long-range view, like Transformers, but efficiently like CNNs.
That's the idea, efficient long-range dependency modeling. And the sources mention MambaYOLO as sort of a first attempt to bring this into object detection.
Right, MambaYOLO.
Yeah, it was important work. They used an SSM-based backbone, set a new baseline, showed it was possible. But according to these notes, it had its own shortcomings.
Okay, what were they?
Well, it was maybe a bit monolithic. It didn't really explore how to synergize the strengths of CNNs and SSMs together within the architecture in a nuanced way. Like, how do you get the local detail and the global context working perfectly in concert? It also apparently lacked some of the more advanced multi-scale feature fusion strategies you need for detecting objects of all different sizes really well.
Ah, okay, so it was a good first step, but didn't fully exploit the potential combination.
Pretty much. And that specific gap, really combining the best of CNNs and SSMs intelligently, is exactly what the sources say MambaNeXt-YOLO is designed to address.
Got it. It's built to be a true hybrid.
Exactly. And the core of that hybrid approach is their first big innovation, something called the MambaNeXt Block.
All right, the MambaNeXt Block, this sounds like a key contribution from the paper, academically speaking. What's its main job?
Its main job is to be a fundamental building block that can simultaneously capture both local features and long-range dependencies. It integrates the CNN approach and the Mamba approach within a single module.
Okay, bring them together. How does it actually do that? The sources mention three parts inside this block.
That's right. So first, you've got a conjunct block. That's your CNN component. Conjunct is known for being good at extracting those fine-grained spatial details, the local patterns.
The local expert Check. What's next?
Next is the SS2D Mamba block. This is where the Mamba SSM comes in. It processes the features like sequences, using that selective state space magic to model the global context, the long-range stuff, efficiently. And again, the key academic point is doing this with a linear time complexity, dodging the transformer's quadratic scaling issue.
Local from Canucks, efficient global from SS2D Mamba. Got it. But how do you stick them together? How do you make sure that information gets combined usefully?
That's the job of the third piece, the ResGate block. The sources describe this as the adaptive fusion part. It takes the outputs from the conducts path and the SS2D Mama path and intelligently merges them.
Adaptive fusion, so it's not just adding them up.
Right, the name gives clues. Res likely points to residual connections, which help gradients flow and information pass through easily. Gate implies gating mechanisms, basically. Learn controls that decide how much influence the local features should have versus the global features, and how they should be combined for the best result. It learns the optimal blend.
Wow. Okay, so the network itself figures out the best way to mix the local and global views at that point.
Precisely. And the ablation studies they did where they tested removing or changing parts offer some really neat insights here. They found, unsurprisingly, that having both ConvNeXt and ResGate was better than just one. But the really interesting finding, maybe even a bit surprising,
Yeah.
was that the best performing setup put the ResGate block before the ConvNeXt block. So ResGate feeding into ConvNeXt, that configuration gave them the highest MAP, 66.2%.
Wait, the fusion part before the local detail part, that sounds backwards. Why would you blend information before extracting the fine details?
I know, right? It feels counterintuitive, but the thinking, based on the sources, is that the ResGate's ability to adaptively weigh or select features based on their broader context might actually prepare or refine the feature map before the ConvNeXt does its detailed local analysis. It's like the ResGate highlights the important areas or relationships first, letting the ConvNeXt focus its efforts more effectively.
Huh. So it's like pre-processing the features with global context before zooming in locally. That's a fascinating architectural detail.
It really showed that the order matters just as much as the components themselves. And those studies also help fine-tune things, like finding that a ConNeXt kernel size of 7 worked best, suggesting a slightly larger local view is beneficial.
Right, bigger receptive field.
Exactly. And for the Mamba part, they found increasing its state dimension, the D-state parameter, helped. It peaked at 66.6% MAP with a D-state of 32. Basically, giving Mamba more memory capacity helps it capture those complex long-range patterns better. These are the kinds of academic details that push the performance up.
Okay, so that's the MambaNeXt block, handling hybrid feature extraction in the backbone. But there's another big innovation mentioned, specifically for dealing with objects of different sizes, right? The MAFPN.
Yes, the multi-branch Asymmetric Fusion Pyramid Network, or MAFPN. Another key academic contribution, focusing on the neck of the detector, the part that fuses features from different layers.
Feature pyramids are crucial for seeing both big and small objects, yeah?
Absolutely. It's a classic challenge. How do you effectively combine the fine details from early layers, good for small objects, with the high-level semantic understanding from deeper layers, good for large objects? MAFPN is their enhanced take on this.
So its goal is better multi-scale detection.
Exactly. Better multi-scale feature representation and specifically strengthening the information flow between different levels of the network, aiming for better accuracy across all object sizes, maybe particularly small ones.
And how does it do that? That name, multi-branch asymmetric, sounds complex.
It's definitely more intricate than a standard feature pyramid network, FPN. Traditional FPNs often have a primary top-down path, bringing high-level context down to low-level features. MAFPN uses asymmetric branches for both the upsampling path, top-down, and a downsampling path, bottom-up.
Ah, so information flows more freely in both directions.
That's the idea. It creates richer connections, allowing fine details to influence high-level understanding and high-level context to refine low-level details more effectively. They use things like asymmetric kernels, reparametized convolutions, even Mamba modules within the MFPN structure itself to achieve this enhanced bidirectional fusion.
Okay, so it's a more sophisticated way to mix features from different scales. And the goals were efficient fusion, better small object handling, and keeping it lightweight.
Correct on all counts, according to the sources.
Did the experiments back up this design choice? Were there ablation studies for the MFPN too?
Yes, and there was a really significant finding there regarding how downsampling was done inside the MAFPN. They compared standard max pooling, just taking the max value in a window, with using stride convolutions, learnable filters that also downsample.
And
Replacing max pooling with stride 2 convolutions for downsampling within the MFPN gave a big performance boost. MA jumped from 63.2% up to 66.0%.
wow, nearly 3 points of MAP just from changing the downsampling method. Why such a big difference?
It comes down to learnability. Max pooling is fixed, non-learnable. Stride convolutions have learnable weights. The sources suggest this leads to more learnable and consistent feature transformations. The network actually learns the best way to reduce the feature map size while preserving the crucial information needed for detection at different scales rather than just applying a rigid rule.
So learned downsampling beats fixed downsampling here. Another interesting insight. Okay, so putting it all together, MambaNeXt blocks in the backbone, MAFPN as the neck. What's the overall structure?
It follows that classic backbone neck-head paradigm. The backbone starts with a stem layer, then stacks of MambaNeXt blocks. Between these stacks, they use a specific downsampling unit.
Right, you mentioned the VCM division clue merge unit earlier. That's for downsampling in the backbone.
Yes, exactly. Its job is to reduce the feature map size between stages in the backbone while trying to hang on to important visual information. The sources say it does this by spatially splitting the features using one-by-one convolutions, concatenating then another one-by-one convolution. It's a specific design apparently carried over from MambaYOLO, and they mention removing normalization layers here to keep it lean.
Okay, so VCM in the backbone for downsampling between stages, and stride convolutions preferred for downsampling within the MAFPN neck. Different tools for slightly different jobs.
Precisely. Then the MFPN neck takes features from multiple backbone levels and fuses them. And finally, there's a lightweight detection head that makes the actual predictions, bounding boxes and classes at 3 different scales of resolutions, usually called P3, P4, and P5.
P3 for small objects, P5 for large, P4 in the middle. Standard stuff there.
Pretty standard head design, yeah. Keeps the final stage efficient.
Okay, we've got the architecture laid out. The big question, how did it actually perform? Especially considering its goal of being good for edge devices.
Right, the evaluation. They tested it on PASCAL VOC and Dodo V1.5 datasets. And a key point the sources emphasize, this was without pre-training on huge datasets like ImageNet. Training from scratch is a harder test.
Good point. So the numbers.
On PASCAL VOC, they had 66.6% MAP, which is the main accuracy metric, and 85.1% AP50, which often relates to how well localized the objects are. Pretty solid.
And on Dota, that's the aerial imagery one, right? More challenging.
Yeah, Dota's tough. Lots of small objects, rotation variations. There, they achieved 27.8% MAP and 43.5% AP50.
How did those compare to other YOLOs or MambaYOLO?
According to the comparison tables in the sources, MambaNeXt-YOLO came out ahead of the baseline models they compared against on both datasets. That includes several recent lightweight YOLOs V8-S, V9T, V10-S, V11-S, V12-S, and also the previous MambaYOLO-T. Achieving 66.6% MAP without pre-training is definitely a strong result for this class of model.
Okay, good accuracy. Now for the speed, especially on the edge, did it deliver there?
This seems to be where the design really shines, validating the whole approach. They tested it on NVIDIA Jetson platforms, common edge AI hardware. On the Jetson Orin NX, it achieved 31.9 FPS while getting that 66.6% MAP.
Whoa, okay. Over 30 frames per second. That is real-time territory, especially with that level of accuracy on an actual edge device.
Absolutely. That's fast enough for many practical applications. They also reported speeds on the older Jetson Xavier NX, 19.5 FPS. And just for context, on a high-end desktop GTU, an RTX 3090, 34.6 FPS. And these edge speeds were measured using optimized Tensor RT inference with FP16 precision, which is standard practice for deployment.
So the results seem to confirm it. They managed to build a model that successfully hits that sweet spot of high accuracy and genuine real-time speed, specifically for resource-constrained environments. The hybrid approach works.
It really looks like it. It demonstrates the practical benefits of combining SSM efficiency with CNN local detail capture. It's not just a theoretical win, it performs well on the target hardware.
So thinking bigger picture now, what are the main takeaways from this research, and where might this lead next?
Well, the big takeaway is really the validation of this hybrid SSM CNN strategy for real-time vision. It shows it's a very effective path forward, especially when computational resources are tight. It proves the philosophy works.
And the researchers have plans to take this further.
They do. The sources mentioned they're looking at extending it to video object detection, which makes sense. Also, multimodal perception, combining vision with other senses like audio or text.
Okay, that seems like a natural progression.
But then they also mentioned something interesting, potential applications in semantic and emotion-driven generation for dialogue systems.
Dialogue systems. From an object detector architecture, that's unexpected?
It is a bit of a leap, but I think it shows how they view the core strengths of the architecture. If it's good at efficient long-range modeling and blending different feature types in vision, maybe that fundamental capability could be useful in other domains that handle complex sequences or need to integrate different kinds of information, like advanced conversational AI. It suggests they see broad potential in the underlying hybrid framework.
Fascinating. So we've gone from the speed accuracy problem in YOLO through the limits of CNNs and transformers, unpacked the clever MambaNeXt block and the MFPN, looked at the structure, and seen these impressive edge performance numbers.
Yeah, it's a really well thought out piece of engineering, combining different ideas effectively.
So maybe a final thought for everyone listening to chew on. MambaNeXt-YOLO really highlights this idea that maybe we shouldn't think of different neural net architectures, CNNs, transformers, SSMs, as competing options, but as potential collaborators. Combining the local smarts of CNNs with the efficient global reach of SSMs, as they did here, seems incredibly powerful, especially when you hit hardware limits. So the question is, what other problems out there, maybe in vision, maybe somewhere else entirely, could benefit from this kind of smart architectural matchup? Where else could blending different network philosophies unlock new capabilities?
It definitely opens up a more combinatorial way of thinking about designing these models. Lots to explore there.
Absolutely. And exploring those kinds of questions is what happens when you take the deep dive.